All right, so we're picking up 1.1 functions. This is part 3. I've already made use of this term several times up to this point, but we're going to get a little bit more into it. We're going to be talking about the domain of a function. So the domain is the set of all inputs. Here we have a nice mapping diagram. The domain here are these input values, -2, 0, 3, 7. This is a discrete set, meaning it's just a finite number of elements in there. Doesn't have to be that way, so we can restrict it arbitrarily and just give a function a discrete set like this and call that the domain. Or it could just be a situation where only certain values make sense. Let's just talk about the area of a square, right? Area equals the side length squared. It only makes sense for certain side lengths, right? We're not going to have any side lengths of 0. That doesn't make sense. Wouldn't make a square. Also wouldn't have any negative side lengths because we just don't talk about length or distance in terms of negative values. So this would be S has to be greater than 0. But, we don't have to say that, just kind of we know that to be case because it only makes sense for those values to be positive. However, some equations may be undefined for some input values. Really simple one, right? F of x equals 1 over x. This is a pretty common thing. There's a particular number here that is a problem, right? X cannot equal 0. Can't divide by 0. That is not mathematically defined, so we have to restrict that value from the domain. It can't be an input. We'll look at some other things that can happen, particularly to equations that would cause us to kind of have a restricted domain of some sort. All right. So that restricted domain for an equation is often referred to with this terminology, the implied domain. It may not be explicitly stated or told to you, but it's something that you need to be able to figure out because you know stuff about equations, you know stuff about math and certain types of operations. So the implied domain of a function is the set of all real number input values for which the function is defined. Technically, functions could have complex inputs or imaginary inputs, but we're going to talk mostly about real number inputs. So here we have this function f of x equals the square root of x minus 3. Seems simple enough. We can plug in numbers. We could plug in 4. Actually, we did that earlier on. Really, we could plug in many, many numbers. But what happens if we try to plug in a number like, I don't know, 0? We'll just take a look at this real quick. F of 0, square root 0 minus 3. Well, that's going to be the square root of -3. That technically we know what that is. That's I root 3 or square root 3i, however you want to say that. Has value, but that's not a real number. We actually say at this point that this is undefined. So our function is not defined, at least on the real numbers for inputs of 0. But 0 is not the only input, right? There's lots of inputs that would be a problem here. Turns out anything that would cause us to be taking the square root of a negative number, anything that would cause this, the argument inside the radicand, inside the radical symbol here, anything that causes this to be less than 0, which is a proxy, another way of saying negative, is a problem. We do not allow that. So our domain needs this to be greater than or equal to 0. Right? 0 or positive. So our domain are all values that satisfy this inequality. Pretty simple inequality to solve. We add 3 to both sides. We get x has to be greater than or equal to 3. This is what we would say is the domain, the implied domain of this function. Values greater than or equal to 3, totally good. Anything smaller than that, get out of here. It's going to cause, us to get an imaginary number. This is kind of the second major thing that happens. Square roots don't want to really be taking the square root of a negative value. We know we can do it, but technically it's not a defined output on the real numbers, and we can't divide by 0. So again, just summary, right? Square roots, anything that causes us to take the square root of a negative, we don't want to allow it. So what's inside the square root, right? The inside must be greater than or equal to 0, positive or 0. We can take the square root of 0 or a positive number. and dividing by 0, right? So our denominator, anytime we have a rational function, the denominator cannot be equal to 0 because that causes us to divide by 0. It's a problem, can't be allowed. So let's go ahead and take a look at these two functions here real quick and try to determine the implied domain. So here, again, this is a square root. We know that we don't want to try to take the square root of negative, so we know that this has to be greater than or equal to 0. Otherwise, it's undefined. So solving this, we simply add 7. Get 2x has to be greater than or equal to 7. Divide both sides by 2. We see that x has to be greater than or equal to 3.5. So this is the way we would talk about our domain. X is greater than or equal to 3.5. Those inputs are allowed. Anything else? Again, get out of here. We don't want to deal with imaginary numbers right now. Okay, let's go ahead and move forward to the second one. Again, denominator, this is a rational function. Anything that causes this denominator equals 0, that's going to be a problem. We have to say those numbers are not allowed. So this cannot equal 0. So we want to figure out what x values do make it 0 and say those are not allowed. Pretty easy here. We could solve this a couple different ways. We could factor it. We could add 16 to both sides, whatever. Let's do adding 16 to both sides. So x squared equals 16. Square rooting both sides, we get x is equal to plus or minus 4. Remember, when you're using the square root operation, like we're doing right here, you have to consider both the positive and the negative root. So x cannot be equal to positive 4 or negative 4. Everything else is fine. All real numbers except these two. This would be our implied domain. All right, let's go ahead and clear this. Let's go ahead and take a look at one more example of this, finding our implied domain. So we have our function f of x is equal to the square root of 10 minus x. Again, this is a simple square root, right? So anything that would cause the inside of this radical symbol here to be negative is not allowed. So we need it to be greater than or equal to 0. So we can solve this in a lot of different ways. I'm going to just go ahead and move this x over to the other side. So this says 10 is less than or greater than or equal to x. Let's just go ahead and flip that around. That means that x is less than or equal to 10. That's our domain. Now, there's a couple different ways that we write domain, and actually we're going to want to understand another way of doing this. So I'm going to sketch out a quick number line here. Just stick 10 in the middle. We're saying that values 10, including 10, that one's fine. So we put a closed dot on that, and less are totally fine. Anything bigger than that, not allowed, not part of the domain. Technically, this goes all the way down to negative infinity. So rather than writing it in this way, which is fine, perfectly fine, there's another way of writing it, which we call interval notation. We want to describe this interval here. So we have a minimum value of negative infinity. Technically, that really means there's no minimum value, and it goes all the way up to 10. We do include 10. 10 is an included value in our domain, so I actually have to use this bracket here. Parentheses and brackets have slightly different definitions, which we'll look at in just a moment. But this is another way of expressing this right here. It means the same thing. X is less than or equal to 10, or the domain is from negative infinity all the way up to and including 10. That's another way for us to say our implied domain here. Anyway, let's take a look at that interval notation. Yeah, let's take a look at interval notation first. We'll go back to that slide in just a second. So interval notation and set notation. So what we were writing before with those inequality symbols, that's often referred to as set notation. But another way of writing it is this interval notation where we use either parentheses or brackets and a minimum value and a maximum value, if they exist, to express our range or our domain. The difference here being we use parentheses when either the minimum or the maximum is not included. We also use that not included. We also use that with infinity, with negative infinity and positive infinity, because technically those aren't really numbers. The number negative infinity, which isn't a number, is not included in our domain. So we use parentheses with that. Or infinity also, right? So if that value is not included. Another situation where it might not be included would be a situation where there's an asymptote, right? It goes all the way up to that value, but it doesn't technically touch it, right? If we have a vertical asymptote on a graph at a particular number, and I'll just say it's at 4, and the graph is like approaching it, right? It goes up to 4, but it technically doesn't touch 4. That's a situation where we would have to use a parentheses. Whereas if the graph does actually stop at a certain number, I don't know, say we have a sideways parabola like this, and this is the farthest left that it goes is our minimum value. I don't know, it's at -2. Well, there's a point there, so that is an included value, so we would use a bracket instead of a parenthesis. So it depends on whether there is a specific point on the graph at that location or not, except in the case of infinity, where that's not actually a number, so we just always use parentheses with those. Anyway, we'll use this a little more here and kind of get used to it. Yeah, let's go back though. All right, so let's find the implied domain of this function right here. G of x is equal to x plus 3 all over x squared plus x minus 20. All right, so again, this is a situation where we have a rational function and we know that the denominator cannot equal 0. Those are the values that have to be restricted from our domain, cut out all numbers except these. Yeah, so we have to figure out, well, what values of x would cause the denominator to equal 0? So we actually just have a simple quadratic equation on our hands to solve. We can solve this however we want, factoring, quadratic formula, completing the square, whatever. I'm going to go ahead and use factoring. So we need to figure out two numbers that multiply to -20 and add to be 1, which is -4 and +5, which means that this quadratic factors as x minus 4 and x plus 5. Okay. Using the zero product property, we can split this up. Since these two factors multiply to equal 0, it will only be true if one or both of the factors equals 0. So x minus 4 equals 0, x plus 5 equals 0. Solve both of these, adding 4 to both sides, we get x equals 4. Subtracting 5 on both sides, we get x equals -5. So both of these values would cause our denominator to equal 0, which means not that x can be equal to, but x cannot be equal to these values, right? These must be restricted from our domain. Couple different ways that we can write this. We could create some crazy intervals and stuff. A lot of things. Usually you will see something like this, all real numbers except x cannot equal -4 or 5, right? Something like, oh, I messed up. Anyway, it's +4 and -5. Fix that, there we go. Something like this could describe it, right? Just talking about what the particular excluded values are. We could also have something like a little bit more complicated. If you could imagine sort of a number line here and say like, ooh, -5 and 4. These specifically are non-included values, but we have all of this is good, everything in between here is good, and everything bigger than 4 is good. So technically we have kind of 3 distinct intervals, and we could write those out using interval notation or inequalities or something like that, right? So this one would say like x is less than -5. This would say that x is between -5 and 4, and this would be something like x is greater than 4. And we have like a combination of all 3 of these intervals. We could write that in interval notation, where we would say something like x is less than -5. That means we're going from -infinity all the way up to -5, not including either of those, because right, that's excluded. Union with this interval here between -5 and +4, again, not including any of those, and unioned with finally this last interval here, starting at 4 is our minimum value all the way up to +infinity, up forever, right? So you could have this kind of crazy interval notation, or you could have this combination of inequalities to express it. Or you could just say something kind of simple like this. All of them are fine. You'll find that something like this is the most common, but these other things could be done. Anyway, let's go ahead and move forward. Let's find the domain of the following function. So here, conveniently, we have a nice graph. Sometimes these things are easier seen graphically. So, I said before in class that, we're going to be using graphing calculators and graphing programs like this Desmos graph here to help things out. But, we can do it both ways. It is important that we can do it both ways also. So we know that this will only be defined so long as whatever's inside of the square root is a 0 or a positive value. So if it's greater than or equal to 0, right? That is the algebraic way to go about this. Solve this inequality. That's your domain. Easier, perhaps, is looking at the graph. You can see that starting at -4 and moving to the right indefinitely, forever. If you kind of had Desmos open, you could zoom this out and see it just keeps going on forever. This graph's defined, right? So starting at -4, including that value, that one's fine. Going all the way to infinity, that's our domain. So it might be easier to look at the graph. It might be easier to do it algebraically. Doesn't really matter. Both are valid methods, and you need to understand both. Anyway, solving this one, right? Subtract 4 on both sides. We should say x has to be greater than or equal to -4, which is the same as this interval that we just described, right? Going from -4 being our minimum value, including it, and going all the way up to infinity, going to the right forever. Okay. Let's go ahead and find the domain of this function. Again, we'll take a look at the graph also, kind of help us see that as well. And we'll take a look at it algebraically as well. This is a rational function, so anything that causes our denominator to equal 0 must be restricted or kept out of our domain, right? So we know this can't equal 0 on the bottom, so we could solve that algebraically. Also, we can sort of see those restricted values show up as apparent asymptotes on our graph. Now, the asymptotes aren't drawn in, but I can put them in there for you. You can see, or you can at least assume that there is one here at -3, right? This looks like asymptote behavior. The graph is both going, going vertical up as soon as it approaches -3. So it's not actually going to touch -3. It's just going to go up and kind of get closer and closer and closer forever. Same thing going on this side. So we know that it's not defined there at x equals -3. And also we can see that it's also not defined here at +3, right? There's another asymptote happening right there at +3. Line's a little crooked, but that's fine. So we know that this graph will not be defined at -3 or +3. All other numbers are fine, but those are restricted values. X cannot be equal to those things. That's exactly what we're going to find here algebraically, right? Those are the two numbers that would cause the denominator to equal 0. 3 squared minus 9, 0, problem, right? -3 squared is 9, minus 9, 0, that's a problem, right? You could factor this, whatever, it doesn't really matter. It's going to give us the same thing, right? Let's just talk about this one. This is a difference of squares. Hopefully you remember that, right? X squared minus 3 squared. So this would factor as x plus 3 and x minus 3. And the values that would make this 0 are -3, right? X equals -3 would cause that to be 0. And 3 minus 3 is 0, so x equals 3. So those are the two values that we can't have. So all real numbers except x equals 3 and x equals -3. Maybe you'll even see somebody write it like this: x not equal to plus or minus 3. Tons of different ways to communicate this idea. Really what we're looking at is what numbers cannot be in the domain, cannot be inputs. And we found them. All right, we'll go ahead and stop right there. We'll talk about difference quotient in part 4, and there you go.